Last, but certainly not least, please welcome on stage Jacob Marks, ML engineer and developer evangelist at Voxel51. Jacob will be leading the session titled Vector Search for Data and Model Understanding.
Thank you. Thank you, everybody, for staying this long. I know this is the last talk of the day. Appreciate you being here. Drinks are after, fortunately for all of us. My name is Jacob, and today I'm going to be talking to you about vector search and how that can help you to understand your data and models better. So my background, I studied physics, got into machine learning about a year ago. I am at Voxel51. Who are we? We are a data-centric AI company. Our mission is to help people to build better data sets so that they can train better models. So we want to increase transparency and clarity for the world's data. Today, I'm going to talk to you about data, and more data, and then a little models. And we're going to talk about how you can use vector search to understand that data. So everybody here has probably heard of RAG, retrieval augmented generation, but they might not know that vector search is actually an incredibly powerful and versatile tool that can be used for so much more than just retrieval augmented generation and large language models. We're currently in the middle of an AI Cambrian explosion. So no matter how you slice it or dice it, there's just an incredible amount of activity and fun stuff and exciting improvements going on in the space. Whether you're talking about the number of papers per month, the size of the best models, or you're talking about the state-of-the-art performance, which is changing incredibly rapidly. It seems like every day there's a new state-of-the-art model for almost any task. But something that people don't really focus on a lot is the fact that data quality is super important for these state-of-the-art achievements. So the difference between the best model and the second best model or the third best model is so small these days that cleaning your data and understanding your data so that you can build a better data set is essential. And that might make the difference between your model being the best and the next runner-up. So some of these issues can be things like label mistakes. They can be duplicates, low quality samples, blurry images. It can be really anything, outliers, anomalies, out of distribution stuff. And this is really the villain of machine learning. Mostly I'm going to be talking about computer vision data, visual data like images, videos, and point clouds. But in general, machine learning, bad data is incredibly nefarious. It can cause model bias issues. It can cause reduction in your performance and even lethal danger when put into production. In other words, data is king. Data is where the model gets its power from. It's what you train it on. It's what you evaluate it on. It's at the center of everything. So we really need to put data at the center of our workflows. We need to be able to filter our data, to clean it, to exclude bad data, to curate a high-quality subset of that data, to select important features, and overall just to understand our data better. So anything that we can do to understand our data better is going to be essential to us to create the best models. So I'm sure you've heard of RAG, but I just want to give a quick overview of how it works. This is from my perspective. The way that retrieval augmented generation happens is when you're interacting with a language model, you give a prompt to the model, and then a lot of stuff happens behind the scenes. That prompt is then processed. You have sometimes you are embedding that prompt. You are finding similar results based on that prompt. You are looking up documentation, and you are feeding in the relevant information into the context of the model. And then the model is then using that information to prevent hallucinations, to do in-context learning, all sorts of stuff. But the key thing that I want to focus on here is that for retrieval augmented generation, the way that you interact with the vector search component of it is indirect. You don't have any direct access to it. It's non-interactive. It is very much that the vector search part is happening on the back end, and you don't really get to think about it or deal with it. Of course, when you're building the system, you have to put a lot of thought into it, but as a user, you don't get to use it. Why does retrieval augmented generation work? What is going on to make this so powerful? Well, there's really two reasons. One is that we are embedding our data. So whether you're talking about text or images or whatever else, we are using some model that is going to take that input data and is going to generate a vector representation of that data that captures some semblance of or some notion about what's going on in the original samples. So here what we have is, in the example, we take this text, bovine buddies say, we run it through a model, and we get this vector, which represents something about the data. And at the top right here, we have a printout of the MTEB leaderboard, and this is just a bunch of different embedding models. Each of them has different strengths and weaknesses. They're changing all the time. The model that you use matters a lot for the way that all the data is represented. And the second reason that this works is vector similarity. So there are different ways of computing the similarity between vectors. You can use an L2 distance, a cosine distance, dot product, you name it. But the general notion is that by looking at how similar your query vector is, so the query for your input to the model, and the text that you have in your database, you can find similar examples and then return those to the user. So basically, the idea is the vectors are similar, so the original inputs should be similar as well. And there are some subtleties here that go into that, but high level, that's the idea. Now, this doesn't just work for text data. This is also true for images. So here we have an example of a model that was trained with an encoder-decoder style, which takes in an image of a bunch of pixels, and then you have some representation in the middle, and then at the end you get a representation that looks kind of like that. You have something that looks like a synthetically generated digit. And the internal representations, the latent space here is capturing some notion of the data itself. And so we can use those to represent what's going on and to do these types of vector searches over image data. We can also do multimodal stuff. So we can't just look at images or text. We can also look at images and text together, or we can look at not just images and text, but image, text, heat map, audio, depth data, and inertial measurement unit data. So there's a lot of work that goes into actually making this happen. So on the left-hand side, we have CLIP, contrastive language image pre-training from OpenAI, where they take pairs of images and text, some of which are designed to be similar, some of which are designed not to be similar, and they train the model to recognize what is similar and what is not similar in this contrastive fashion, and they embed the images and text into the same space. On the right, we have ImageBind by Meta, and they did this for 5 modalities at the same time. Slightly different methodology, but they were able to embed so that now you can compare your image embeddings to your text embeddings, and this allows you to, and not just text and image, but also audio and IMU and heat map, so you can compare all of these in a somewhat apples-to-apples fashion. It's not going to be perfectly apples-to-apples, but it's going to be somewhat apples-to-apples. Now, here I'm saying computer vision, but I really mean all visual data and just the way that we interact with data more dynamically. The way that I'm going to talk about this interactivity is as follows. So you collect and process your initial data, then you need to understand it, you use that to train a model, and then you go into this feedback cycle. So you need to deploy a model, then you find problems with the model. Maybe there's places the model's underperforming, maybe there's edge cases you didn't consider. You update your data set to reflect those changes. Either you add more data for places that you had issues, or you omit an entire subset because you don't want to consider those things. Then you go back and forth and you continue this process. There's 2 places in this whole workflow where we need to be interactive with our data. We need to interact with the data in the understanding and curation phase. And then during this cycle, we need to be interacting with the data to understand the problems that are occurring along the way. And for both of those things, there's a lot of traditional data understanding techniques that we can use. Not only vector search, but vector search can be useful here if we want to interact with the vector search and expose it directly to ourselves, the users. So what I'm going to show you now is 10 of my favorite applications of vector search for data understanding and exploration, and also in many cases, model understanding and exploration. And these are just 10 that I love and that I was able to think of, but there's so many more, and these are expanding and growing every day. We're going to start simple with image similarity search. You take an image from your data set, you select it, and you find similar images to that from across your data set. So what it's doing here is it is taking the embedding that you have for that image, and it is doing a vector search across the data set that you have, and it is finding the k most similar images by their vectors and returning that to you. Pretty basic. Here's another one. This is reverse image search, so it's very similar to what I just showed you, but in this case, you are using a query image that is not in the original data set. So you can drag and drop this from your computer, you can type in a URL. Really, it's any image that is outside of the data set. Maybe you're dealing with NSFW stuff and you don't want to have that in the data set, but you want to use an example to show the model or see what is in your data set. Here you can do that. At query time, you're embedding that image, and then you're comparing that query embedding to your data set, to the vector database associated with your images. You can even do this for objects. So sometimes the entire image might contain a lot of information. It might have really varied scenes, a lot of people and cars and things in them, but it might be helpful for you to look at the individual objects that you have detected. You can choose your object detection model and treat those individual object patches as their own images of sorts, and then try to do a similarity search on those. So one example that's really common is if you wanted to do facial recognition or person re-identification or something like that, oftentimes it helps to narrow down the scope to the person in that image as opposed to trying to do this over the entire image. And in a similar vein, this is something that you guys have probably seen in another context. People are very often these days taking their documentation and making it searchable. So they'll have a command line interface for this, or they'll create a Voxel app, and you'll be able to search through the company's documentation or your docs or whatever. This is just showing you how easy it is to do this with the notion and the methodology that I am talking about here, where you basically treat each of these blocks of text from OCR, optical character recognition, or however else you want the text to be generated, and you treat them all as their own patches in the same way that we did with the detections in the object detection example. And you can do a similarity search on your text query with respect to those patches and see which pages in your PDF document matched that semblance. So this is my thesis, and I just OCR'd it, and I typed in some text, and I can find the relevant pieces of my thesis. You can do semantic search, so you can, I mentioned you can compare text and images. This is something that's incredibly useful in the early stages of your data exploration. So before you have any labels in your data whatsoever, maybe you're starting to run some zero-shot models, but even before you do that, it might be helpful to just start exploring your data by typing in text queries and seeing what comes up. You can explore different variations on the same text query and see how densely or sparsely populated in certain areas of that space your data set is. So here I'm typing in animal and I'm getting a result, or I'm typing in zebra and I'm getting a bunch of zebras, and that shows me that my data set has a lot of zebra-like objects in it. And you can do things like cross-modal retrieval. So I mentioned image bind, and this is using image bind here. How do we play the, sorry, do I just hit play, or? Do I just advance? Okay. Mouse over? I do have the mouse over. Let me try this. Okay, so this is using image bind, and so I'm using an audio file as a query. So I'm passing in this audio file, and then I can play it. Here's audio of a train, and then it is using image bind to embed the audio and comparing that to my vector index of images. And this is a toy example. A lot of these are toy examples because I'm just doing this for show, but you can think about how this could be applied in your real use cases. This is a fun one, so probing perceptual similarities. So there's a notion in the way that humans perceive the world called perceptual similarity, where if you take a reference image and you take two other images, A and B, and you ask a human to decide which of those two choices is more similar to the reference image, you can get a sense for how humans are perceiving the world, what they think is actually similar to what else. And you can test how a model perceives these things as well. You can train models to try to replicate the way that humans sees the world in that way. And you can see by looking at different models, so this is looking at a couple of models. Some models like CLIP are more semantic, so they'll get the high-level interpretation of what you're typing in. Some of them are very pixels and patches, so things that are more traditional computer vision like convolutional neural nets, which operate on the level of the individual pixels, and the regions around them are going to get the textures right, but they're not going to get the semantics necessarily right. They'll give you maybe a bowl of ramen when the query that you had, the image that you searched with respect to, was a steak, just because the palette that it was on was the same. You can even, this is another model here. This is showing you what the CLIP model thinks of the world. So in this case, the background in a lot of them is bamboo instead of the same as it was in the other ones, but it's getting the interpretation right. This is another fun one, so you can compare model representations. So this is taking two sets of embeddings. We have two models. Model A, we're generating a vector index with, and model B, we are taking these embeddings and dimension reducing them. You can use whatever technique you like. I used UMAP in this case, but you can use TSNE or PCA if you like, and reducing it to 2 dimensions so that you can visualize all of the points and kind of connect them to the images, these samples, and you can do this lasso selection and get a set of these results that are all similar according to one model. And you can do a similarity search with the other model and see where those points pop up in this visualization of the other model. So you can see that there's a difference between the models that are seeing the world, how they're seeing the world, because those points are not clustered together in that space. And then I'm going to end on 2 that are a little bit more experimental, but I think that they are just a proof of concept in the new ways that we can explore and understand our data, all of this experimentation that we still have to do. So in this case, I call this concept interpolation because you're taking the text for a husky and for a chihuahua, and you are somewhere interpolating with some linear combination of the 2 concepts by proxy by taking the embeddings for the text prompt husky and the embedding for the text prompt chihuahua and combining those in the vector space and doing a sort by similarity with respect to that combined vector. So you can choose the weighting and you can kind of see what is going on in your data set and what is closest to that combination. And here's one more in that vein. So I call this one concept space traversal, and again, you can be as mathematically rigorous as you want with these things. These are just for show, but there's a lot of research that actually goes on into how to be rigorous about the way you actually move through this space of embeddings. But the idea here is that you start with an image, and you can add concepts to it dynamically. So you can add the concept for healthy, and you can add that in some amount, and you can go along the vector for that concept, and you can then add another one, in this case colorful, and you can continue and you can add the vector for that concept in some amount, and then you can, with that destination vector, search your data set for similar samples. So you can see what, as you combine concepts from multiple modalities together, your data set includes. So those are just some of my favorite examples. I'm sure you can think of your own. The point of this is not to say these are the best ways. It is to say this is an incredibly exciting opportunity, and we are thinking about the world in a limited fashion if we are just considering retrieval augmented generation when we see these very powerful tools like vector search. The toolkit that I used to do all of these illustrations was 51, which is, in a nutshell, an open source tool set for curating and visualizing your data, finding hidden structure, evaluating models, and it's connected to the entire machine learning ecosystem. Data curation. This is non-vector search related data curation. Data visualization, like I showed you before. So you don't need vector search to do these types of things, but you can select a little grouping of samples and you can see what the model thinks of the world. You can see that that cluster is roughly a bunch of plated food. And you can do fine-grained evaluation. So you can go beyond your one-number metrics, and you can get results on the level of individual samples and individual predictions, and then you can visualize those and filter and query by them. So what I showed you was using our vector search integrations. We have native integrations with all of these vector search tools. This is all open source, and you can use any of these things with our open source toolkit. And if you liked this, we have 2 more events coming up very soon. So on Sunday, I will be doing a talk with Deep Learning AI on an intro to this toolkit, and then we will have a Getting Started workshop on the 6th. So thank you to Google for hosting this. Thank you to DevFest and Google Developer Groups, and that is it from me. If you have questions, do it into the mic. I think they're recording.
Thank you. Regard like when you classify the images as a healthy or whatever, can you use a scale to compare 2 images?
Can you use a what?
A scale.
A scale?
Yeah. Or like, let's say, if you want to take a photo or a photo of arrowhead, a small, like maybe 2 centimeter or something, and it could be similar to something like 5 meter. How we could distinguish between these 2 objects with the size or the scale of that object?
So if you're talking about objects at different scales, you may not need vector search. You may be able to just use inherent properties like the number of pixels across that image or the bounding box size or whatever else you want. I think that gets into other questions around computer vision, not necessarily vector search. But as long as you have good enough resolution on those, the way that a lot of these models basically process the images is they will downsize them to like 224 pixels in one dimension. So if you have more than that, then it will just like cut it down to that, and it will treat them all as the same.
So Voxel51 itself is just a vector search engine, or is it just using other vector search compare vector database?
So Voxel51 is the company. 51 is the tool set for building better data sets and curating that data to train better models. We integrate with all these vector search tools, and I was showing you how you can use vector search as a powerful vehicle for doing this exploration. That is something that integrates with our tool set. That is not the only thing that we do.
I'm just wondering how public provided data versus expert provided data just works together, just as you scale this thing in business. So you showed us expert training of data, and then we see things like gamification, like capture code graphics. We have to click all the zebra crossings, or emoji games. I think there was one that was mentioned in another thing. What do you see as which one is more important? Which one is more likely to be more common? Which just what as this and which one will provide more business value, etc. I'm just wondering how the two play together.
Yeah, great question. And I will caveat this that I do not consider myself an expert in this, and everybody has their own opinion. But what I have seen and what we see a lot at Voxel51 is that to get high performance, you need really high quality special purpose data. So either that's you finding existing data and paring that down to just the data you want, sometimes augmenting that, or it's you actually going out and collecting that data yourself from your real world use case or from some other way. You can use off-the-shelf models. They're often a good starting point. You can use foundation models. You can do knowledge distillation and things like that, transfer learning. But in general, the data is probably the most important thing for a lot of real-world applications and not just trying to build the hypiest general purposes thing. Cool. Thank you. Drinks on me.